Hi everyone. We are going to talk about rational exponents. Okay, remember a rational number is a fraction and an exponent is a power. So we're going to talk about what does it mean when I have a number and it's raised to the power of a fraction. What does that mean and how do I work with these? We're going to spend 2 days in this section because there's a lot to cover and I want you to feel really comfortable with it. It's not as hard as it looks once you get what everything means. So let's deal with rational exponents and see if we can figure this out. So here's a basic formula you could put in your notes if you want to. If I have the nth root of x, nth root of some number, then to write that same exact expression in rational form instead of radical form, I would have this base x to the power of 1 over this index. For instance, if I have the square root of 36, then that's the same as 36 to the power of 1 over 2. So now you know something to the power of 1/2 is the same as its square root. So something to the power of 1/3 would be the same as its cube root. Something to the power of 1/4 would be the same as its fourth root. Pretty cool. So let's say you're asked to simplify 216 to the power of 1/3. So this means since it's to the power of 1/3, it's the same as the third root of 216. And right away you're going to flip to that 3x5 card that you filled out to look to see if there's any cube root factors of 216, and lo and behold, 6 to the power of 3 is 216, right? This is 6 cubed. Well, I'll leave that there. The cube root of 6 cubed, and so therefore I can bring my 6 out, and this equals 6. So 216 to the power of 1/3 equals 6. By the way, you're going to want to know, you're going to say, Mrs. K, can my calculators do this? Absolutely. You may have to go 216 to the power of, and then put 1 divided by 3 like that for your 1/3, especially graphing calculators, and it should come up 6. Okay, let's simplify this. I have 7 to the power of 1/2 times 7 to the power of 1/2. Remember, to the power of 1/2 is the same as the square root. So if I think about it as a square root, this is saying the square root of 7 times the square root of 7, right? Which is the square root of 49, or 7. If we're thinking about exponents, since I have this same base, the base is the same, I should have 7 to the power of, what's 1/2 plus 1/2? It's 1. Same answer. Here's another we're asked to simplify. 5 to the power of 1/4 times 125 to the power of 1/4. Just to show you what that would look like as a radical, and then we're going to do it both ways. As a radical, that would be the fourth root of 5 times the fourth root of 125. Since those are both fourth roots, remember we can multiply that, and 5 times 125 is 625. So we have the fourth root of 625, which happens to be 5. If we're just dealing with these rational exponents, because these are both 1/4, I can multiply 5 times 125, just like I could multiply these because the indexes were the same. And I still get 625 to the power of 1/4, which is 5. Okay, so now that we've got an introduction into how the basics of rational exponents, let's see how you do. Let's simplify these things. What is 64 to the power of 1/2 simplified? What is 11 to the power of 1/2 times 11 to the power of 1/2? What is that? And what's 3 to the power of 1/2 times 12 to the power of 1/2? So hopefully you already have those figured out. The 64 to the power of 1/2 is the same as the square root of 64. This is 8. And this is the same as the square root of 11 times the square root of 11. This is 11. And this is the same as the square root of 3 times the square root of 12. 3 times 12 is 36, so the square root of 36 is 6. That's how to simplify those. How did you do? Okay, that was kind of nice and easy because in all those fractions, my exponents, my numerator was always 1. But of course, things don't stay easy for very long, do they? You could have a numerator different than 1, and what would that mean? And so now I'm going to explain that. So let me show you just with the letters. I don't know if this will help or make it worse, but let's say I have some kind of base. I'll call it A, and it's being raised to the power of m over n. Okay, we already know this denominator is our index, right? It's what root it is. This is the root. The numerator is the power. So basically this means A, this root, the nth root of A to the power of m. So here we have, this is the, n is the root, the index, m is my power. Do you see that? It can be written like this inside the radical, or same, it could be the nth root of A raised to that degree. Either way is how it looks. So let's look at this now with numbers and variables. Let's say I'm given this in exponential form and I'm asked to change it to radical form. So if they ask that, notice it's in exponential form. I've got this exponent. Now they want it in radical form. They want to have a radical box around it. So my base is 7. So I've got my radicand is 7. The root is 7. The power is 3. And you can write it like that, or you can write it like this, the 7th root of x raised to the power of 3. Either one is fine. That's how you would change it to radical form. Wow, look at this one. Now I don't even have a fraction. I have this decimal and it's negative. What in the world do I do with that? What we're going to do, since we're dealing with fractions, we're going to take it out of decimal form and put it as an improper fraction. So 3.5 is 7 over 2. So this is going to become 7 over 2, and it's negative. So y to the power of negative 7 over 2. Do you remember negative exponents are saying, help, 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 I'm on the wrong side of the fraction bar. You need to invert it. That negative exponent means invert it. Put this below 1 like this, and it becomes y over 7 over 2, or 1 over y to the power of 7 over 2. Okay, I'm changing this to a radical box, to a radical. That 2 means square root, so I have 1 over the square root of y to the power of 7. I'm not going to leave it like this because this is not in the simplest form. I have to rationalize the denominator. So first let's reduce this. Let's simplify it. Remember, this is a 2. How many 2's are in 7? There's 3. So I can take out 3 y's, y cubed, and I'm left with 1 y down below. Now I still need to rationalize my denominator, so I need to multiply the numerator and the denominator by the square root of y. And now my numerator becomes the square root of y, and my denominator becomes y to the power of 4. Because I have 3 y's, y to the power of 3, times 1 more y is y to the power of 4. And there's my final answer, and that was a doozy. Let's say I'm given the radical form of an expression and I'm asked, what is this in exponential form? So now I'm going to change it from the radical to the exponential. This is a, so a is my base. The power is 5. The root is 2. Remember, it's power over the root. So this is a to the power of 5 over 2. When you have just a plain square root, that's a 2 is the index. Here's another one we've been asked to change to exponential form. I'm going to do this one step by step so that you can kind of see why it is the way it is. The fifth root of b is the same as b to the power of 1/5, right? And if I take that and raise that to the power of 3, you see it's 1/5 times 3, and that's why your final answer is b to the power of 3/5. That's your answer there, and that's it gives you an idea of why it works the way it does. Okay, just a couple more practice, just because I think it's a little complicated. I have this in exponential form. What is this in radical form? And especially this one with the negative and all that. Does that mean? Because we'll probably have to rationalize this one. This one I think will be simpler. But let's start with this. Remember, this is the root, this is the power, and it's negative. So first, this is 1 over w to the power of 5/8, and this is the 8th root of w to the 5th, so 1 over the 8th root of w to the 5th power. Now, in order to rationalize that, I have 5 w's already, but I need a total of 8 in order to get rid of this radical. So I am going to multiply this by the 8th root, got to be the same root, of w to the power of 3. That way, when I'll multiply it, I'll have the 8th root of w to the 8th. Nice. That would be the same as 8 over 8, which would just be w, and that's what I want. But I also have to multiply my numerator by the same thing. So when I simplify this, I end up with the 8th root of w cubed over w. Whew. Okay, let's do the other one, w to the power of 0.2. The first thing to do is to change that into a fraction. 0.2 is 2/10 or 1/5, so this is w to the power of 1/5. So my power is 1, my root is 5, so that's just the 5th root of w to the power of 1, 5th root of w. That one was much easier. Okay, there's a fun word type application problem in your textbook on how to approximate the period it takes for a planet to go around the sun one whole time. Okay, for us it's 1 year. That's how we mark our time, a year. About how long in Earth years does it take some of the other planets? And it really depends on the distance from that planet from the sun. These numbers are so big that they use things called astronomical units, AUs, to do that, and they put the distance in AU terms. So they take that distance to the power of 3 over 2, and that gives you approximately the period of time in Earth years it takes that planet to circle the sun. Can you figure that out? Yes, your calculator can do that. So what you do is you take this distance, an AU distance, and you take whatever that distance is, you write that number in, and in your calculator you go to the power of, and this fraction you treat as 3 divided by 2. You hit enter, and it will tell you, boom, your answer, the time it takes that planet to circumnavigate the sun. Let's walk through their example that they have in the book, which is Mars. Okay, Mars is about 1.52 astronomical units from the Earth. So what you would do is take 1.52 to the power of 3 over 2, and which basically means the square root of this number cubed, doesn't it? Yeah. But you just put the to the power of 3 over 2 in your calculator and see what you get. Your calculator should give you about 1.87. So it takes about 1.87 or a little over 1 3/4 years, right, for Mars to go all the way around the sun. Okay, we're going to finish with your lesson check. I want you to find out the length of a Venusian year. How long does it take Venus to circle the sun? And also a Jovian year. I think I'm saying that right. How long does it take Jupiter to go around the sun? If Venus has astronomical unit of 0.72, how long is, what's its year like in Earth years? And if Jupiter has an astronomical unit of 5.46, then how many years, what's its year in Earth years? How long is that year for that planet? So bring those in for your lesson checks. You should be able to do that with any calculator, should be able to do that for you. But that shows that you watched this video. And next time we will finish this section, work some more on exponential radicals. All right, so bye for now.